Hello there, and welcome to the Sleeping Scientist channel. I'm so glad you're here. Maybe it's been a long day, or maybe you just like to fall asleep thinking about stars, galaxies, and the quiet mysteries of the universe. Either way, tonight's journey is for you. Before we get started, I'd love to know where you are watching from in the comments below. Now let your body rest, your mind slow down, and your thoughts drift. Because tonight, we're exploring exoplanets. Not just one galaxy or star, but the exoplanets. We'll move gently from fact to fact, learning about exoplanets. Some things may surprise you. Others may stay with you like a quiet thought at the edge of sleep. And if these calm explorations help you rest, feel free to like and subscribe. It helps others find their way here too. Let's begin. There are more planets than stars in the galaxy. Let that settle in for a moment. Every point of light you see when you look up at night, every distant star scattered across the darkness, has worlds orbiting around it. Most of them, anyway. And not just one world per star, but entire systems of them, billions upon billions of planets drifting through space, most of which we'll never see, never visit, never even detect. The universe is crowded with silent worlds, and tonight, we're going to drift through some of the most fascinating ones discovered so far. Not to study them or analyze them, but just to let their existence wash over you like a gentle tide. Because there's something deeply calming about knowing that out there, far beyond the noise and rush of daily life, entire planets are simply existing, spinning, orbiting, waiting. Let's start with a number that might surprise you. Scientists have confirmed over 6,000 exoplanets so far, 6,000 worlds beyond our solar system, each one different, each one with its own story written in starlight and gravity. And that's just what we've found in a relatively tiny region of the Milky Way, within a few thousand light years of Earth. The actual number, the true count of planets in our galaxy alone, stretches into the hundreds of billions, maybe even a trillion. We're surrounded by worlds we can't see, orbiting stars we can barely make out, forming systems we're only beginning to understand. The journey began in 1995. That's when astronomers discovered the first exoplanet orbiting a sun-like star, a world called 51 Pegasi b, located about 50 light-years away. It wasn't the first planet ever found outside our solar system, but it was the one that changed everything. Before that discovery, scientists assumed that planetary systems would look more or less like ours. Rocky planets close to the star, gas giants farther out, everything arranged in neat, predictable patterns. But 51 Pegasi b shattered those assumptions completely. This planet, later given the more formal name Dimidium, is a hot Jupiter. That's the term scientists use for gas giants that orbit incredibly close to their stars. And I mean close. Dimidium completes a full orbit around its star in just 4 Earth days. 4 days. It's a massive world, comparable in size to Jupiter, but it races around its sun at blistering speeds, its atmosphere heated to thousands of degrees by the intense radiation. The discovery earned its finders the Nobel Prize in Physics, and it should have. They'd opened a door to an entirely new understanding of how planets form and where they can exist. What makes exoplanets so fascinating isn't just their existence, it's their variety. Scientists have found worlds that defy every expectation, planets that shouldn't exist according to our old models, systems arranged in ways that seem almost impossible. There are hot Jupiters like Dimidium, scorching giants that orbit closer to their stars than Mercury orbits our sun. There are Neptunian worlds, ice giants wrapped in thick atmospheres of hydrogen and helium. There are super-Earths, rocky planets several times more massive than our own world, filling a size category that doesn't exist anywhere in our solar system. And then there are the water worlds. Imagine a planet where oceans cover the entire surface, not oceans like Earth's, with continents breaking through and shallow coastal shelves. but a global sea that might stretch hundreds or even thousands of kilometers deep. No land anywhere, just water, pressing down under its own immense weight, creating layers of high-pressure ice at the bottom despite the heat from the planet's core. Some scientists think these water worlds might be common in the galaxy, and several candidates have already been identified. Kepler, 62f, Kepler 452b, Kepler 442b. Each one a potential ocean world, its surface hidden beneath clouds, its depths holding secrets we can only guess at. The detection methods are remarkably clever. Most exoplanets are found using something called the transit method. Scientists point telescopes at distant stars and watch for the tiniest dimming in their light, a shadow that passes across the star's face when a planet moves between us and its sun. The dimming is incredibly subtle. We're talking about changes in brightness of less than 1%, sometimes far less, but it's enough. By measuring how much light is blocked and how long the transit lasts, scientists can calculate the planet's size, its orbital period, even get hints about its atmosphere. Other planets are detected through the wobble they create in their parent stars. As a planet orbits, it doesn't just circle the star circles too, very slightly, pulled by the planet's gravity into a tiny dance. By watching for this wobble, astronomers can infer the presence of planets they can't see directly, measuring their mass and orbit through the gravitational signature they leave behind. Now let me tell you about a planet that's been around longer than almost anything else in the universe. PSRB 1620-26b is approximately 12.7 billion years old. The universe itself is only 13.8 billion years old, which means this planet formed when the cosmos was still in its infancy, less than a billion years after the Big Bang. It's a gas giant, similar in size to Jupiter, but it orbits in one of the strangest systems we've ever found. Its parent star isn't a normal star at all. It's a pulsar, the incredibly dense remnant of a star that exploded in a supernova. And that pulsar is locked in orbit with a white dwarf, another stellar corpse. The planet circles both of them, tracing a long, slow path around this bizarre binary system. Think about everything this planet has witnessed. It existed before our sun formed. It was already ancient when Earth first coalesced from dust and gas. It was drifting through space when the first single-celled organisms appeared in Earth's oceans, when dinosaurs walked the land, when humans first looked up at the night sky and wondered what was out there. This planet has seen the entire history of our world play out while it continued its patient orbit around two dead stars, a silent witness to cosmic time. But not all exoplanets are lonely wanderers around dying stars. Some exist in systems that feel almost familiar, systems that remind us of home in unexpected ways. The TRAPPIST-1 system contains 7 Earth-sized planets, all orbiting a dim red dwarf star about 40 light-years away. When this system was discovered in 2017, it immediately captured attention. 7 worlds, all rocky, all roughly the same size as Earth. The entire system is remarkably compact. You could fit all 7 planets inside the orbit of Mercury with room to spare. They're packed so tightly that from the surface of one planet, you'd be able to see the others in the sky, not as distant points of light, but as actual disks, visible worlds hanging in the alien heavens. 4 of these planets orbit in what scientists call the habitable zone, the region around a star where temperatures might allow liquid water to exist on a planet's surface. That doesn't guarantee these worlds have water, or atmospheres, or anything resembling life. But it makes them interesting. It makes them worth studying. Because if liquid water can exist there, if conditions are right, then maybe, just maybe, life could exist there too. The star at the center of this system, TRAPPIST-1, is an ultra-cool dwarf. It's much smaller and dimmer than our sun, burning with a dull red glow. From the surface of TRAPPIST-1e, the most Earth-like planet in the system, the star would appear about 4 times larger than the Sun appears from Earth, casting everything in a perpetual reddish twilight. The light would be mostly infrared, not the bright visible spectrum we're used to, and the landscape would be illuminated in soft, muted tones, like standing outside just after sunset, but all the time. These planets are likely tidally locked, meaning the same side always faces the star, just like the Moon always shows the same face to Earth. One hemisphere would experience eternal day, baked by constant starlight. The other would be locked in endless night, cold and dark. The only temperate zones might be the twilight bands in between, the narrow regions where day meets night in an eternal sunset. Scientists have been studying TRAPPIST-1 intensely since its discovery, using instruments like the James Webb Space Telescope to search for signs of atmospheres. So far, the results are inconclusive. Some planets might have atmospheres, others might not. The star itself is volatile, prone to flares and bursts of radiation that could strip away any protective atmospheric layers. It's a harsh environment, especially for the innermost worlds. But the outer planets might be more sheltered, more stable, better protected from the star's violent outbursts. And here's something that adds another layer of intrigue to the TRAPPIST-1 system. The planets aren't just sitting there, static and unchanging. They're interacting with each other gravitationally, tugging and pulling as they orbit. This creates something called tidal heating. As the planets flex and deform under these gravitational forces, friction generates heat deep in their interiors. It's the same process that keeps Jupiter's moon Europa warm enough to maintain a liquid ocean beneath its icy crust. On the TRAPPIST-1 worlds, tidal heating could melt rock, drive volcanic eruptions, power geological activity. Heat doesn't just come from the star above. It comes from within, from the constant gravitational massage these planets experience as they orbit their sun and circle each other in their compact dance. The concept of the habitable zone is helpful, but it's also a simplification. Scientists originally defined it as the region where a planet could have liquid water on its surface, too close to the star, and water boils away in a runaway greenhouse effect. Too far, and it freezes solid. But we've learned that habitability is more complicated than distance from a star. Internal heat sources matter. Atmospheric composition matters. Even the planet's history, the impacts it's endured, the way its surface has evolved over billions of years, all of that plays a role. Some worlds might be habitable even outside the traditional zone. If a planet has enough internal heat from radioactive decay or tidal forces, it could maintain subsurface oceans even in the frozen outer reaches of a solar system. Jupiter's moon Europa does exactly this. So does Saturn's moon Enceladus. These worlds are nowhere near the habitable zone as traditionally defined, yet they have liquid water, energy sources, and possibly the chemical ingredients for life. They're habitable in their own way, hidden beneath shells of ice, protected from the radiation and cold of deep space. And then there are worlds that should be habitable, but aren't. Venus sits right at the inner edge of our sun's habitable zone, but its surface is hot enough to melt lead, crushed under an atmosphere 90 times thicker than Earth's and filled with sulfuric acid clouds. Mars sits at the outer edge, but its thin atmosphere and lack of a magnetic field have left it cold and dry, its surface scoured by radiation. Distance from the star matters, but it's not everything. Habitability depends on a delicate balance of factors, many of which we're only beginning to understand. Let me bring you back to something closer to home, at least in cosmic terms. Proxima Centauri b orbits the nearest star to our solar system, just over 4 light-years away. In the grand scale of the universe, 4 light-years is practically next door. It's still an unimaginable distance by human standards. If you traveled at the speed of the fastest spacecraft we've ever built, It would take tens of thousands of years to reach Proxima Centauri b. But in astronomical terms, it's close. Close enough that scientists are seriously discussing the possibility of sending robotic probes there someday. Tiny spacecraft accelerated by lasers to a fraction of light speed, reaching the system in just a few decades. Proxima Centauri b is probably rocky. It orbits within its star's habitable zone, though like the TRAPPIST-1 planets, it faces challenges. Proxima Centauri is a red dwarf, smaller and dimmer than the Sun, but also more active, prone to flares that could make the surface of any nearby planet a harsh, radiation-soaked environment. Still, the possibility exists. Liquid water might be there. An atmosphere might shield the surface. Life, if it arose, might have found a way to survive. The exoplanets discovered so far represent just the beginning. Most of what we've found orbits within a few thousand light-years of Earth, a tiny fraction of the galaxy's 100,000 light-year span. As our detection methods improve, as new telescopes launch and new techniques develop, that number will grow. 6,000 confirmed exoplanets will become 10,000, then 50,000, then more. Each discovery will add another piece to the puzzle, another data point in our understanding of how planets form, where they can exist, and what conditions might support life. But for now, tonight, the number is 6,000. 6,000 worlds confirmed, billions more waiting to be found. Some of them are hot Jupiters, scorched giants racing around their stars. Some are super-Earths, rocky worlds larger than our own. Some might be water worlds, their surfaces hidden beneath global oceans. And some might be places where, against all odds, life has found a foothold in the darkness between the stars. There's something unsettling about thinking of worlds where the sun never truly rises, where the landscape exists in permanent twilight, bathed in the faint infrared glow of a star so dim it barely registers as light. That's the reality for many planets orbiting red dwarf stars. These stellar embers, far smaller and cooler than our Sun, are the most common stars in the galaxy. 3 out of every 4 stars you see belongs to this category. And if their planets can harbor life, the implications are staggering. Red dwarfs burn slowly. So slowly that many formed in the early universe are still shining today, and will continue to shine for trillions of years into the future. Long after stars like our Sun have exhausted their fuel and collapsed into white dwarfs, red dwarfs will still be here, patient and enduring. Their longevity offers a peculiar advantage. Life, if it emerges on a planet orbiting a red dwarf, has time. Billions upon billions of years to evolve, adapt, and perhaps develop into forms we can't yet imagine. But there's a cost to orbiting these dim stars. To receive enough warmth for liquid water, a planet must orbit extremely close. So close that tidal forces lock it in place, one face perpetually turned toward the star, the other facing eternal night. The division creates extremes. The day side scorches under constant radiation. The night side freezes in endless darkness. Between them, along the terminator line where day meets night, conditions might be more forgiving. A narrow band where temperatures balance, where liquid water could pool, where life might cling to existence in the twilight zone between fire and ice. Then there are the flares. Red dwarfs may burn slowly, but they're far from calm. These stars are prone to violent outbursts, eruptions of high-energy radiation that blast across their planetary systems without warning. For a planet orbiting close enough to be warm, these flares are devastating. They strip away atmospheres, bombard surfaces with radiation, and create environments hostile to life as we understand it. Yet some models suggest that a thick enough atmosphere or a strong magnetic field could provide protection. The question remains open. TRAPPIST-1's planets face this challenge. Located 40 light-years away, this system of 7 Earth-sized worlds orbiting a red dwarf has become one of the most studied exoplanetary systems in existence. Early observations with the James Webb Space Telescope targeted TRAPPIST-1d, the third planet from the star. The results were inconclusive. No clear signs of an atmosphere, but also no definitive evidence that one doesn't exist. Thick clouds could be hiding it, or the planet might simply be a barren rock, stripped by stellar winds long ago. The uncertainty is frustrating, but it's also revealing. Every observation teaches us something, even when the answer isn't clear. Scientists are learning how to probe these distant atmospheres, how to distinguish between different scenarios, how to separate signal from noise in the faintest glimmers of light. Each data point brings us closer to understanding whether planets around red dwarfs can maintain the conditions necessary for life. Consider the mechanics of tidal locking for a moment. It's not instantaneous. When a planet first forms, it spins freely, rotating on its axis just like Earth does. But gravity is patient. The star's pull creates bulges in the planet's crust, subtle distortions that shift as the planet rotates. Over millions of years, these tidal forces act like brakes, slowing the rotation until the planet's spin matches its orbital period. One face becomes permanently day, the other permanently night. This process generates heat, enormous amounts of it. The constant flexing and stretching of the planet's interior as it's pulled by its star and neighboring planets creates friction. That friction melts rock, drives volcanic activity, and could potentially create subsurface oceans, even on worlds too cold for surface water. On some of the TRAPPIST-1 planets, tidal heating might be more significant than the heat received from the star itself. Internal furnaces warming worlds from below, independent of their star's feeble light. Now shift your focus to a different kind of world entirely. Water worlds, planets where oceans cover the entire surface, potentially hundreds or even thousands of kilometers deep. No continents, no islands, just water, extending from pole to pole and down into crushing depths where pressure transforms the ocean floor into exotic forms of ice that exist nowhere on Earth. These aren't science fiction. Current observations suggest that several confirmed exoplanets might fit this description. Kepler 62f, Kepler 1652b, Kepler 442b. Their densities and compositions hint at enormous water content, far exceeding anything in our solar system. Earth's oceans are deep, but they're a thin film compared to the global seas these worlds might possess. The habitability of such planets is debated. Traditional thinking suggests life requires land, that the carbon-silicate cycle, driven by weathering of continental rocks, is essential for regulating atmospheric carbon dioxide over geological timescales. Without this cycle, a planet's climate might spiral out of control. Too much carbon dioxide leads to runaway greenhouse heating. Too little, and the planet freezes. But recent models challenge this assumption. Water worlds might maintain stable climates through different mechanisms. Their atmospheres could naturally settle into what researchers call a sweet spot for carbon dioxide levels. Not through active cycling, but through the sheer presence of vast oceans and the specific way water worlds trap and release gases. If true, these planets could remain habitable for billions of years without any land surface at all. Imagine standing on such a world. There's no shore to walk along, no beach where waves lap at sand. The horizon in every direction is water, extending to the planet's curvature and beyond. Beneath your feet, the ocean might be kilometers deep, perhaps tens of kilometers, possibly hundreds. At those depths, pressure becomes extreme. Water behaves strangely under such conditions. It can become denser than ice, creating layers of high-pressure ice at the bottom, even though the temperature is warm. These exotic ice layers, designated Ice 6, Ice 7, or even Ice 10, exist in states that have no analog on Earth's surface. And below that, possibly a rocky core, or perhaps more water still. compressed into states where it conducts electricity like metal. The boundary between ocean and interior might not be sharp at all, but a gradual transition through phases of matter we've only studied in laboratories. Life on a water world would be fundamentally aquatic. No emergence onto land because there is no land. No forests or grasslands or deserts. Just the ocean, shallow at the top where light penetrates, dark in the depths where only bioluminescence breaks the blackness. Evolution on such a planet would follow paths very different from Earth's. Perhaps intelligent life could arise in those alien seas, civilizations that never knew the concept of dry ground, but built their societies in the currents and pressures of an endless ocean. The search for these worlds drives much of current exoplanet research. Scientists have developed techniques to analyze the light filtering through a planet's atmosphere as it passes in front of its star. This method, called transmission spectroscopy, reveals the chemical composition of the air. Water vapor leaves distinct signatures. So does carbon dioxide, methane, oxygen, and countless other compounds. By studying these spectral fingerprints, researchers can determine not just whether a planet has an atmosphere, but what that atmosphere is made of. The James Webb Space Telescope has revolutionized this field. Its infrared sensors can detect molecules that were invisible to previous instruments. It peers through dust clouds, sees through atmospheric hazes, and captures light from planets that would have been impossible to study just a decade ago. Early results are already reshaping our understanding of exoplanet atmospheres, revealing unexpected chemistry and raising new questions about how these distant worlds formed and evolved. Take WASP 96b, a hot Jupiter about 1100 light-years from Earth. Webb's observations of this planet revealed clear signatures of water vapor in its atmosphere, along with evidence of clouds and haze. The data showed sodium absorption, confirming earlier ground-based observations but with unprecedented detail. This wasn't just detecting that water exists, it was measuring how much, at what altitudes, and how it interacts with other atmospheric components. That level of precision was unthinkable before Webb launched. Or consider WASP 39b, another hot Jupiter that Webb studied in exquisite detail. The telescope detected carbon dioxide in its atmosphere, the first definitive detection of this molecule on an exoplanet. It also found sodium, potassium, water vapor, and even hints of photochemistry. Chemical reactions driven by starlight that alter the atmospheric composition in real time. These observations revealed that WASP 39b's atmosphere is far more complex than simple models predicted, with multiple layers, varying temperatures, and dynamic weather systems. But the truly exciting targets are the smaller, rockier worlds. Planets like the TRAPPIST-1 system, where conditions might be right for life. Webb has begun studying these worlds too, though the results are mixed. Some planets show no clear atmospheric signatures. Others remain ambiguous, the data open to multiple interpretations. The challenge is immense. These planets are small, their atmospheres thin, and the signals they produce are faint. Extracting meaningful information requires patience, repeated observations, and sophisticated analysis techniques. Still, progress continues. Each observation refines our methods. Each dataset teaches us how to distinguish between different atmospheric scenarios. Slowly, carefully, the picture is becoming clearer. Some rocky exoplanets definitely lack thick atmospheres. Others might have them, hidden behind clouds, or composed of molecules that are difficult to detect with current instruments. And a few perhaps will reveal themselves to be worlds where conditions truly do resemble Earth's. The nearest candidate remains Proxima Centauri b, 4 light-years away, orbiting the closest star to our solar system. It's rocky, probably. It orbits within the habitable zone, possibly. But Proxima Centauri is a red dwarf, active and violent. known for flares that could strip away any atmosphere the planet once possessed. Recent studies have attempted to determine whether Proxima b retains its air. The results are inconclusive. Some models suggest it could, protected by a strong magnetic field or a thick initial atmosphere that could withstand the stellar assault. Others predict a barren surface, scoured by radiation over billions of years. We won't know for certain without better observations, or perhaps eventually a visit. Proxima Centauri b is the most realistic target for an interstellar probe, assuming humanity develops the technology for such a journey. Concepts exist. Proposals for tiny spacecraft accelerated to a fraction of light speed by powerful lasers, reaching the system in just decades rather than millennia. They would be simple probes, carrying cameras and basic instruments, beaming back images and data as they fly past. No landing, no detailed study, just a glimpse. But what a glimpse it would be. The first close look at another star's planets. The first direct images of an alien world's surface. That moment, if it comes, will mark a turning point. The transition from speculation to observation, from wondering about distant worlds to seeing them directly. Until then, we study them from afar, piecing together their stories from the light they reflect and the shadows they cast. Each observation adds detail to the picture, fills in gaps in our understanding, and points toward the next question that needs answering. And there are many questions. How common are Earth-like planets? How often do they retain atmospheres around red dwarfs? How much water is too much for life? Can tidal heating create habitable zones in unexpected places? What other factors influence habitability that we haven't yet considered? The field of exoplanet science is still young, barely 3 decades old. We've discovered thousands of worlds, but we've only begun to understand them. The next decades will bring clearer answers, more sophisticated observations, and perhaps the discovery that will change everything. The detection itself might come sooner than you expect, not from a telescope image, but from something more subtle. The chemical signature of life, hidden in the spectrum of an atmosphere 40 light years away. Biosignatures, that's the term astronomers use. Molecules that, in significant quantities, suggest biological activity. Oxygen is the classic example. Not oxygen alone, but oxygen combined with methane in the same atmosphere. This pairing is chemically unstable. The two gases react together unless something continually replenishes them. On Earth, that something is life. Photosynthesis produces oxygen. Microbes produce methane. Together, they create a signature that wouldn't exist on a sterile world. Finding this combination on an exoplanet would be compelling, not conclusive, necessarily. Nature can produce surprising chemistry without biology, but it would warrant serious attention, detailed follow-up observations, and careful analysis of alternative explanations. The James Webb Space Telescope can detect some biosignatures, in theory. In practice, it's challenging. The signals are weak. The observations require many hours of telescope time focused on a single target. And Webb wasn't specifically designed for this purpose. It's a general-purpose infrared telescope that happens to be capable of exoplanet atmosphere studies, among many other tasks. Future missions will be more specialized. NASA has proposed the Habitable Worlds Observatory, a telescope designed specifically to study potentially habitable exoplanets. It would use a coronagraph or starshade to block the star's light, allowing direct observation of the planets themselves. This technique, called direct imaging, would enable detailed spectroscopic analysis of their atmospheres without waiting for transits. Such observations could reveal not just oxygen and methane, but more complex biosignatures. Dimethyl sulfide, for instance, a molecule produced by marine phytoplankton on Earth, or combinations of gases that indicate active surface chemistry inconsistent with geological processes alone. But here's what makes this search particularly fascinating. we might detect life on a planet we'll never visit, never send a probe to, never receive a signal from. The detection would be entirely passive, based on analyzing light that traveled for decades across space. And yet it would fundamentally alter our understanding of our place in the universe. Consider the implications. If life exists on multiple exoplanets within a few dozen light years of Earth, life must be common. Not rare, not unique to our world. Common enough that it appears on several of the few planets we can study in detail. That would suggest billions of living worlds throughout the galaxy, perhaps trillions. The nature of that life remains unknown. Microbes, almost certainly. Complex ecosystems, possibly. Intelligence? That's far more speculative. But even microbial life on another world would answer one of humanity's oldest questions. Are we alone? The answer would be no. This possibility drives much of the current research. Scientists are developing models of different atmospheric compositions, predicting which biosignatures might appear under various conditions. They're studying Earth's own atmosphere throughout its history, noting how biosignatures have changed as life evolved. Early Earth had methane but no oxygen. Later Earth had oxygen but less methane. The balance shifted as photosynthetic organisms transformed the planet. Other worlds might show different patterns, different chemistry, different atmospheric balances, indicating different forms of life. A planet dominated by methane-producing organisms, but lacking photosynthesis, would look different from Earth. A world with purple vegetation instead of green would reflect light differently. These variations expand the range of biosignatures we might detect, but they also complicate interpretation. False positives remain a concern. Geological processes can mimic biological ones. Volcanoes produce gases. Photochemistry in atmospheres creates unexpected molecules. Lightning generates compounds that might otherwise suggest life. Distinguishing between these non-biological sources and true biosignatures requires careful analysis and, ideally, multiple independent lines of evidence. That's why detecting oxygen and methane together matters more than detecting either alone. The combination is harder to explain without biology. Similarly, finding multiple biosignatures simultaneously would strengthen the case. One unusual molecule might have a geological explanation. Several unusual molecules, all present in quantities inconsistent with known chemistry, would be far more compelling. The search extends beyond habitable zone planets too. Scientists are investigating whether subsurface ocean worlds might harbor life. Europa, Saturn's moon Enceladus. These bodies are too far from the sun for surface liquid water. But tidal heating keeps their interiors warm, maintaining vast oceans beneath ice shells kilometers thick. Similar moons might exist around exoplanets. A large gas giant in the habitable zone wouldn't be habitable itself, but its moons could be, protected by their planet's magnetosphere, warmed by tidal forces. They might host conditions suitable for life, despite orbiting far from their star. Detecting life on such moons would be even more challenging than detecting it on planets. Their atmospheres are thinner, their signals weaker, but ongoing research suggests it might be possible. Given sensitive enough instruments and enough observation time, water worlds present another intriguing possibility. These are planets with oceans hundreds or thousands of kilometers deep, covering their entire surface. No continents, no exposed rock, just water, all the way down until pressure transforms it into exotic forms of ice. Some scientists argue these worlds might be ideal for life. Abundant water, stable conditions, protection from radiation. Others suggest they might be too uniform, lacking the geological recycling that enriches Earth's biosphere. The debate continues, informed by new observations of candidate water worlds. Kepler 452b is often mentioned in this context. Similar in size to Earth, orbiting a sun-like star in the habitable zone. Its density suggests it might contain significant water, but we don't know for certain. More detailed observations are needed to constrain its composition and determine whether it truly is a water world or something else entirely. The diversity of exoplanets continues to surprise researchers. Mini-Neptunes dominate the discoveries, planets between Earth and Neptune in size. Our solar system has nothing like them. They're the most common type found so far, yet we have no local example to study up close. What are these worlds like? We're not entirely sure. Some might be rocky planets with thick hydrogen atmospheres. Others could be water worlds with modest gas envelopes. Still others might be icy bodies, frozen but with compositions unlike anything in our solar system. Each new observation refines our understanding slightly, but major questions remain. Super-Earths occupy a similar grey area. Larger than Earth but smaller than Neptune, they could be rocky, icy, or something in between. Their internal structure depends on their formation history, which we can only infer from their current properties. Some might have plate tectonics like Earth. Others might be single-plate worlds with very different geological cycles. Hot Jupiters, meanwhile, continue to defy easy explanation. These massive gas giants orbit incredibly close to their stars, completing circuits in days or even hours. How did they get there? Planets don't form that close to stars. The environment is too hot, too energetic. The prevailing theory suggests they formed farther out, then migrated inward through interactions with the protoplanetary disk or with other planets. But migration alone doesn't explain all their properties. Some hot Jupiters orbit retrograde, moving opposite to their star's rotation. This suggests violent past interactions, possibly close encounters with other planets that flung them into their current orbits. The resulting systems are dynamically strange, with planets in configurations that seem barely stable. Studying these extreme worlds helps us understand planetary formation more broadly. If giant planets can migrate, what does that mean for the stability of planetary systems over time? How common are planetary ejections, collisions, orbital disruptions? Our solar system seems relatively calm, but is it typical? Early observations suggested our system might be unusual. The first exoplanets discovered were hot Jupiters and other extreme configurations. This created the impression that solar systems like ours were rare, but this was observational bias. Large planets close to their stars are easiest to detect. As techniques improved, smaller, more distant planets began appearing in the data. Now the picture is more balanced. Solar systems similar to ours probably aren't rare, but neither are they dominant. There's tremendous variety in how planetary systems arrange themselves. Some have hot Jupiters, others have chains of mini-Neptunes. Some have widely spaced planets. Others have tightly packed systems where planets orbit closer together than Mercury orbits our Sun. This diversity reflects different formation pathways. The composition of the protoplanetary disk matters. The presence or absence of nearby stars influences development. The timing of planet formation relative to disk dispersal affects the final architecture. Every system has its own story, shaped by countless small variations in initial conditions. Understanding these stories requires studying many systems. That's why discovery continues, despite having already found thousands of planets. Each new detection adds another data point, another piece of the puzzle. Patterns emerge from the accumulation of examples. Theories become testable against large samples. The Transiting Exoplanet Survey satellite has been particularly valuable for this statistical work. By surveying the entire sky, it provides an unbiased sample of planets around nearby stars. This allows astronomers to measure how common different types of planets are, how their frequency varies with stellar type, and whether certain configurations are linked to specific star properties. Results from these surveys are rewriting textbooks. The galaxy contains far more planets than anyone anticipated. Nearly every star hosts at least one planet. Many have multiple. The total number of planets in the Milky Way probably exceeds 1 trillion. That's more worlds than humans have names for. More planets than we could visit even with millions of years and faster than light travel. Most of these planets remain unknown. We've detected a tiny fraction, those close enough and large enough for current instruments to find. As telescopes improve, the number will grow, but we'll never catalogue them all. The galaxy is too vast. Even with perfect instruments, there's not enough time to observe every star, measure every transit, confirm every signal. That's not the goal anyway. The goal is understanding. How do planets form? How often do conditions arise that could support life? What factors determine whether a planet becomes habitable or hostile? These questions don't require detecting every planet. They require detecting enough planets to discern patterns and test theories. We're approaching that threshold now. The sample size is large enough that statistically significant conclusions can be drawn about planet populations. Not about individual systems, necessarily, but about the galaxy as a whole. We can say with confidence that Earth-sized planets are common, that rocky planets in habitable zones exist around billions of stars, that the universe is filled with worlds where conditions might just possibly be right. Turning possibility into certainty requires better observations. The next generation of telescopes, both ground-based and space-based, will provide that capability. Larger mirrors, more sensitive detectors, longer observation periods. The combination will reveal details currently hidden in the noise. Atmospheres will be characterized with precision. Clouds, hazes, and weather patterns will become observable. Surface features might be detected through subtle variations in reflected light. For the closest and most favorable targets, we might even map rough surface geography, distinguishing continents from oceans, ice caps from temperate zones. This is where the search for life becomes concrete. Not just detecting biosignatures, but understanding the worlds that produce them. Are they ocean planets, desert worlds with isolated water reserves, planets with active geological cycles? The context matters. Life on Earth thrives because of Earth-specific conditions. Life elsewhere will reflect its own world's unique properties. Imagination fills the gaps that observation hasn't yet reached. We picture forests under red suns, oceans beneath ice, microbes in volcanic vents on worlds we'll never see. Some of these imaginings will prove accurate, others will be wildly wrong. But all of them reflect the fundamental shift in perspective that exoplanet discoveries have created. The universe is not barren. It's populated with worlds beyond counting, each following its own story, each shaped by physics and chemistry and time. Some are dead rocks, others might be living, breathing, evolving systems. We're learning to tell the difference. The discovery of exoplanets didn't just expand our inventory of known worlds, it fundamentally altered the way we think about planets themselves. Before 1995, planetary science was built on a sample size of exactly 8, 9 if you counted Pluto. That's not much to work with when trying to understand how planets form, evolve, and arrange themselves around stars. It's like trying to understand biodiversity by studying only the animals in your backyard. The first exoplanet around a sun-like star changed everything. 51 Pegasi b, discovered in October 1995, was nothing like the planets in our solar system. This gas giant orbited its star in just 4 Earth days. 4 days. Mercury takes 88 days to complete its orbit, and we consider that fast. 51 Pegasi b orbited so close to its star that its atmospheric temperature exceeded 1,000 degrees. It defied every model of planetary formation that existed at the time. Gas giants weren't supposed to form that close to stars. They needed cold conditions, abundant volatile materials, the kind of environment found only in the outer reaches of solar systems. But there it was, a hot Jupiter, as astronomers came to call this new class of planet. Not just possible, but real. The discovery earned its finders the Nobel Prize in Physics. More importantly, it opened the floodgates. If gas giants could orbit close to their stars, what other configurations were possible? What other planetary arrangements might exist that we'd simply never imagined? The answer turned out to be nearly everything. Hot Jupiters became just one category among many. Warm Neptunes appeared next. Planets similar in size to Neptune or Uranus, but orbiting at distances where their hydrogen and helium atmospheres remain stable despite elevated temperatures. Then came the super-Earths, worlds 2 to 10 times Earth's mass that don't exist anywhere in our solar system. Super-Earths fill a curious gap. Our solar system jumps from Earth-sized rocky planets to Neptune-sized ice giants. Nothing in between. But in the galaxy at large, super-Earths turn out to be incredibly common. Perhaps the most common type of planet there is. What are they like? That depends on their composition. Some are rocky planets scaled up, massive terrestrial worlds with thick atmospheres and potentially active geology. Others are mini Neptunes, gas-rich worlds that lost their hydrogen envelopes or never accumulated them in the first place. Still others might be water worlds, ocean planets where liquid covers the entire surface to depths of hundreds or thousands of kilometers. We don't have examples to visit. All super-Earths discovered so far orbit distant stars. But their prevalence suggests that Earth-sized planets might actually be the unusual case, the lower end of a size distribution that peaks somewhere around 5 to 7 Earth masses. The variety extends beyond size and composition. Orbital configurations span an enormous range. Some planets circle their stars in days. Others take centuries. Some orbit backward, moving opposite to their star's rotation. Some have wildly elliptical orbits, swinging from scorching proximity to frozen distance and back again. Binary star systems host planets too, worlds that orbit both stars simultaneously, experiencing dual sunrises and sunsets like something from science fiction. Or planets that orbit just one star in a binary pair, remaining stable despite the gravitational influence of a second sun nearby. Multiple planet systems are common, stars with 3, 4, 5 planets or more. Some of these systems are tightly packed, with planets spaced so closely that their mutual gravitational interactions create complex orbital resonances. Others are spread out, more like our own solar system's architecture. TRAPPIST-1 represents an extreme case. 7 Earth-sized planets orbit this dim, red dwarf star, all packed into a space smaller than Mercury's orbit around our Sun. The entire system could fit comfortably inside the distance between Earth and the Sun. Despite this compact arrangement, the system appears stable, with the planets locked in gravitational resonances that prevent collisions. 4 of these planets orbit in or near the habitable zone. TRAPPIST 1, D, E, F, and G receive the right amount of starlight for liquid water to potentially exist on their surfaces. The star itself is cooler and dimmer than our Sun, so planets must orbit much closer to receive equivalent energy. But the principle remains the same. Distance from the star determines temperature, and temperature determines whether water stays frozen, liquid, or boils away. TRAPPIST-1e matches Earth most closely. Similar mass, similar radius, similar density. It receives about 60% the starlight Earth gets, but that might be enough. Its orbit takes just over 6 Earth days, completing nearly 60 revolutions in the time Earth completes one. The star looms large in its sky, appearing 4 times the angular diameter of our Sun, glowing deep red. One complication, TRAPPIST-1e is probably tidally locked. The same side always faces the star, like how Earth's moon always shows us the same face. One hemisphere experiences permanent day, the other permanent night. The day side bakes under constant starlight. The night side freezes in eternal darkness. Can life exist on a tidally locked world? That depends on whether an atmosphere can redistribute heat. A thick atmosphere with strong winds might transfer warmth from the day side to the night side, creating a twilight zone between the two extremes where temperatures remain moderate. Without that heat transfer, the planet would be divided into uninhabitable extremes. Recent observations from the James Webb Space Telescope couldn't definitively determine whether TRAPPIST-1e has an atmosphere. The data fit multiple models. Either the planet is bare rock with no atmosphere at all, or it has an atmosphere hidden beneath thick clouds, or something in between. Further observations will narrow the possibilities. The uncertainty reflects a broader challenge. Detecting exoplanets is hard, characterizing them is harder, and determining habitability is hardest of all. Most exoplanet discoveries come from the transit method, watching for the tiny dimming of starlight when a planet crosses in front of its star from our perspective. This method works well for finding planets, especially large ones in close orbits, but it provides limited information: size, orbital period, sometimes density, if we can also measure the planet's mass through its gravitational tug on the star. That's about it. To learn more, we need spectroscopy. When starlight passes through a planet's atmosphere during transit, some wavelengths are absorbed by atmospheric gases. By measuring which wavelengths are missing, scientists can identify the chemical composition of the atmosphere. Water vapor, methane, carbon dioxide, oxygen, each leaves a distinct signature. This technique works, but it requires incredibly precise measurements. Planetary atmospheres are thin. The amount of starlight they absorb is minuscule. Detecting that absorption against the background noise of stellar variability and instrumental limitations pushes current technology to its limits. The James Webb Space Telescope helps. Its larger mirror and superior infrared sensitivity make it better suited for atmospheric characterization than any previous instrument. Early results are promising. Atmospheric compositions have been measured for several exoplanets, confirming the presence of water, methane, and other molecules. But these are mostly large planets, hot Jupiters and warm Neptunes where the atmospheric signals are stronger. For Earth-sized planets, the challenge remains steep. Their atmospheres are thinner, their transits dimmer, their atmospheric signatures fainter. JWST can study them, as the TRAPPIST-1 observations demonstrate, but the data quality is marginal. Definitive conclusions require multiple observations, careful analysis, and often remain ambiguous. That's why the search for biosignatures focuses on the most favorable targets, planets close enough for detailed observation, orbiting dim enough stars that the planet's signal isn't overwhelmed by stellar light, with orbits aligned so we can observe transits. Even with those constraints, the sample size is small. Proxima Centauri b represents the closest known exoplanet, just over 4 light-years away, orbiting the nearest star to our solar system. It's a rocky planet, probably Earth-sized, orbiting in the habitable zone of its red dwarf star. On paper, it's an ideal target for study. In practice, it's complicated. Proxima Centauri is an active star, prone to violent flares that blast the planet with high-energy radiation. These flares might strip away any atmosphere the planet once had, leaving bare rock exposed to space. Or the atmosphere might persist, protected by a strong magnetic field, or constantly replenished by volcanic outgassing. We don't know yet. The planet also doesn't transit from our perspective. We detect it through the radial velocity method, measuring the star's wobble as the planet's gravity tugs it back and forth. That tells us the planet exists and provides a minimum mass estimate. But without transits, we can't study its atmosphere directly. We can only speculate based on models and comparisons to similar systems. The question of habitability extends beyond atmospheric composition. Internal heat matters too. Earth's habitability depends partly on plate tectonics, which recycle carbon dioxide and regulate climate over geologic timescales. Does Proxima Centauri b have plate tectonics? Does it have a molten core generating a magnetic field? These factors influence long-term habitability, but remain unobservable with current technology. Tidal heating adds another variable. Planets in close orbits experience strong gravitational forces that flex and squeeze them as they move. This flexing generates internal heat, warming the planet from within. On TRAPPIST-1's inner worlds, tidal heating might melt mantles and drive intense volcanism. On outer worlds, it could maintain subsurface oceans beneath frozen crusts, similar to Jupiter's moon Europa. Water worlds complicate the picture further. Some exoplanets appear to have enormous amounts of water, far more than Earth's oceans. If that water exists primarily on the surface, these worlds would be covered by global oceans hundreds or thousands of kilometers deep. No continents, no exposed land, just water, all the way down until pressure and temperature create exotic forms of ice despite the heat. Can life exist on a water world? Maybe. Earth's oceans teem with life despite lacking land. But Earth's life depends on nutrient cycling, driven partly by continental weathering. Water worlds lack that mechanism. Their biospheres, if they exist, would function differently. How differently remains unknown. The diversity of exoplanets suggests that the concept of habitability might be narrower or broader than we think. Narrower because many planets that fall within traditional habitable zones might still be uninhabitable due to atmospheric composition, tidal locking, stellar activity, or other factors. Broader because some planets outside habitable zones might harbor life in subsurface oceans or exotic environments we haven't considered. Ancient planets add another dimension. PSRB 162-0-26b is estimated to be 12.7 billion years old, nearly as old as the universe itself. It orbits a pulsar and white dwarf, stellar remnants left after violent deaths. The planet somehow survived those catastrophes, persisting through supernova explosions and gravitational upheaval. How common are such ancient survivors? If planets can endure stellar death and continue existing for billions of years around exotic remnants, the possibilities expand considerably. Life might arise not just on planets around main sequence stars like our Sun, but on worlds orbiting white dwarfs, neutron stars, or even black holes, if conditions permit. The sheer number of planetary environments means that even unlikely scenarios might occur frequently in absolute terms. If 1 in a million planets develops life, and there are trillions of planets in the galaxy, then millions of living worlds exist. The challenge is finding them among the vast majority of barren rocks, toxic atmospheres, and frozen wastelands. Statistical studies help narrow the search. By examining large samples of planets and correlating their properties with stellar characteristics, scientists identify patterns. Certain types of stars host certain types of planets more frequently. Some orbital configurations are common, while others are rare. These patterns guide observational priorities, focusing limited telescope time on the most promising candidates. Red dwarf stars dominate the galaxy numerically. 3/4 of all stars fall into this category. They're smaller, cooler, and longer-lived than Sun-like stars. Planets orbiting red dwarfs must orbit closely to remain warm enough for liquid water, but close orbits mean tidal locking and exposure to stellar flares. Despite these challenges, red dwarf systems might host the majority of habitable planets, simply because red dwarfs are so numerous. If even a small fraction of their planets maintain atmospheres and stable climates, the absolute number could exceed habitable planets around Sun-like stars. Human perspective shapes these considerations in subtle ways. We search for Earth-like conditions because Earth is our only example of a habitable world. But life elsewhere might thrive under conditions we consider hostile. High pressure, extreme temperatures, exotic chemistry. These might not preclude biology, just different biology. The next phase of exoplanet science will test these assumptions by gathering data from as many diverse worlds as possible, characterizing their atmospheres, measuring their properties, and searching for patterns that reveal fundamental principles. Remaining Part 5. Outline. Characterizing individual exoplanets through detailed atmospheric studies, biosignatures, technosignatures, false positives in biosignature detection, and philosophical implications. Atmospheric characterization represents the frontier. When starlight passes through a planet's atmosphere during transit, molecules absorb specific wavelengths, leaving fingerprints in the spectrum. By analyzing these absorption lines, scientists can identify chemical compounds present in alien skies. Water vapor, methane, carbon dioxide, oxygen. Each leaves a unique signature. The technique sounds straightforward, but execution proves challenging. Atmospheres are thin compared to planetary diameters, so the signal is weak. Distinguishing planetary atmospheric features from stellar activity, instrumental noise, and contamination from our own atmosphere requires careful analysis. Multiple observations build confidence, separating real signals from artifacts. The James Webb Space Telescope brings unprecedented capabilities to this work. Its infrared sensitivity allows detection of molecules that previous instruments couldn't observe. Its larger mirror collects more light, improving signal strength. Early results demonstrate what's possible. TRAPPIST. One observations revealed that at least one planet in that system likely lacks a thick atmosphere, constraining models of atmospheric retention around red dwarfs. Other observations detected water vapor, carbon dioxide, and sulfur dioxide in exoplanet atmospheres, mapping chemical compositions across diverse worlds. Each detection adds a data point. As the sample grows, patterns emerge. Hot Jupiters show different atmospheric chemistry than cooler Neptune-sized worlds. Planets orbiting close to their stars often have atmospheres stripped or chemically altered by stellar radiation. Rocky planets in habitable zones might maintain atmospheres if conditions favor atmospheric retention over geological time. These patterns inform theoretical models and guide future observations toward the most promising targets. Biosignatures represent the ultimate goal. Could we detect life on an exoplanet from light years away? The concept relies on identifying gases that life produces in quantities that non-biological processes cannot easily maintain. On Earth, oxygen dominates the atmosphere because photosynthetic organisms continuously replenish it. Without life, oxygen would react away over geological timescales. Finding oxygen in an exoplanet's atmosphere might indicate biology, but it's not that simple. Oxygen alone doesn't prove life. Photodissociation of water vapor can produce oxygen without biology. A planet losing its oceans to space might accumulate oxygen in its atmosphere. As hydrogen escapes and oxygen remains behind. This false positive scenario must be ruled out before concluding that oxygen indicates life. Scientists look for combinations of gases instead. Oxygen plus methane creates a stronger case because these gases react with each other. Maintaining both simultaneously requires continuous replenishment, which biology provides on Earth. Finding this combination would suggest similar processes elsewhere. Methane itself is ambiguous. Geological processes produce methane through serpentinization and volcanic outgassing. Biology produces methane through methanogenesis, a metabolic pathway used by many microorganisms. Distinguishing biological from geological methane requires context. If methane appears alongside other biosignatures in an atmosphere that seems otherwise conducive to life, the case strengthens. If methane appears alone on a world with active volcanism, geology might explain it. Phosphine emerged as a controversial biosignature candidate when tentatively detected in Venus's atmosphere. On Earth, phosphine is produced by anaerobic bacteria and industrial processes. No known abiotic process on rocky planets efficiently produces phosphine in significant quantities. Its detection on Venus sparked debate about whether life might exist in the planet's clouds, where conditions are less extreme than at the surface. Subsequent observations cast doubt on the initial detection, highlighting how difficult it is to make definitive claims from limited data. The phosphine controversy illustrates broader challenges. Instruments have limitations. Data requires interpretation. Atmospheric chemistry on alien worlds might differ from terrestrial experience. What seems impossible based on Earth might be commonplace elsewhere. Caution is warranted, but so is openness to unexpected findings. As observational capabilities improve, distinguishing between these possibilities becomes more feasible. Technosignatures offer another avenue. Instead of searching for biological gases, look for signs of technology. Radio signals, laser pulses, industrial pollutants, or megastructures might reveal civilizations that have developed technology. This approach targets a different question. Not whether life exists, but whether intelligent, communicative life exists. The distinction matters because technological civilizations might be much rarer than simple microbial life, making detection less likely but more profound if successful. CT, the search for extraterrestrial intelligence, has monitored radio frequencies for decades, searching for artificial signals. No confirmed detection has occurred, but the search continues with improving sensitivity and expanded frequency coverage. Optical SETI looks for brief laser flashes that might represent interstellar communication attempts. Both approaches assume that any civilization trying to communicate would use methods detectable across interstellar distances. Atmospheric technosignatures provide another angle. Industrial civilizations produce pollutants. Chlorofluorocarbons on Earth are entirely artificial, produced by refrigeration and aerosol industries. Their presence in an exoplanet's atmosphere would be difficult to explain through natural processes. Similarly, large-scale engineering projects might alter atmospheric composition in ways that reveal technological activity. These signals would persist, even if the civilization no longer exists, creating a kind of archaeological signature visible across space. The concept expands the search beyond active communication. Civilizations might not broadcast intentionally, but still leave detectable traces of their existence. A sufficiently advanced civilization might undertake projects visible at interstellar distances. Dyson spheres partially enclosing stars, planetary-scale engineering, or interstellar probes. While speculative, these ideas provide frameworks for what to look for and how to interpret anomalies that don't fit natural explanations. False positives haunt biosignature detection. Distinguishing life from non-life based on atmospheric chemistry alone requires understanding all possible non-biological pathways that might produce similar signals. This is difficult because our knowledge of planetary chemistry remains incomplete. New discoveries about geological processes, photochemistry, or exotic mineral interactions might reveal abiotic pathways to molecules previously considered biological. Oxygen provides the clearest example. For decades, oxygen was considered a strong biosignature. Then models showed that water vapor photodissociation on planets losing their oceans could produce oxygen-rich atmospheres without biology. This realization didn't invalidate oxygen as a biosignature, but added nuance. Context matters. Is the planet actively losing water? Does it have a magnetic field protecting its atmosphere? Are other gases present that support a biological interpretation? The full picture determines the conclusion. Methane faces similar issues. Serpentinization, a process where water reacts with iron-rich rocks, produces methane without biology. This occurs on Earth in certain geological settings and might be common on water-rich exoplanets. If a planet has active tectonics and abundant water, geological methane production could be substantial. Distinguishing geological from biological methane requires isotopic analysis, looking at the ratio of carbon-12 to carbon-13, which differs between biological and geological sources. This level of detail pushes the limits of current technology, but might be achievable with future instruments. Dimethyl sulfide, another candidate biosignature, is produced by marine phytoplankton on Earth. Its detection in an exoplanet atmosphere would suggest oceanic life. But could geology produce it? The question remains open. As each potential biosignature is examined, scientists discover edge cases and ambiguities that complicate interpretation. This doesn't mean the search is futile, only that it requires care, multiple lines of evidence, and willingness to consider alternative explanations. The philosophical implications of finding life extend beyond science. If life exists elsewhere, questions about its origin, evolution, and nature become urgent. Is life a universal phenomenon arising wherever conditions permit? Or is it exceedingly rare, with Earth representing a cosmic fluke? The answer shapes how we understand our place in the universe and the likelihood of life beyond the few worlds we can currently study. Universal biology suggests that life arises naturally from chemistry under the right conditions. If true, the galaxy might teem with living worlds, each following similar biochemical principles. Water-based chemistry, carbon compounds, and energy gradients might universally drive the emergence of self-replicating systems. Variations would exist, different biochemical pathways, alternative genetic codes, diverse metabolisms, but underlying principles might remain consistent. Alternatively, life might be a rare accident. Perhaps the transition from chemistry to biology requires conditions so specific and improbable that it happens only once in billions of worlds. If Earth is unique or nearly so, the implications are profound. It places extraordinary responsibility on humanity to preserve life because we might be the only instance of it. It also makes the search for extraterrestrial life less likely to succeed, not because we're searching poorly, but because there's little to find. These possibilities can't be resolved through philosophy alone. Observations provide answers. Finding even microbial life elsewhere, especially if it arose independently of Earth life, would strongly support universal biology. Finding complex ecosystems or intelligent civilizations would make the case even stronger. Conversely, decades of searching without finding anything might suggest life is rare, though absence of evidence isn't evidence of absence. Panspermia offers a middle ground. Perhaps life originated once and spread through space via meteorites, comets, or interstellar dust. Microorganisms might survive in space, enduring radiation and vacuum, then seed new worlds when they land. If true, life elsewhere might share a common origin with Earth life, making it less surprising to find, but no less significant. Panspermia doesn't explain life's original emergence, but distributes it across multiple worlds, increasing the odds of finding it. Characterizing exoplanets requires balancing optimism with rigor. Every detection, every spectrum, every data point contributes to understanding. But each also carries uncertainty. Instruments have noise. Models have assumptions. Nature has complexity we haven't anticipated. Progress comes from acknowledging these limitations while pushing forward with better technology, refined methods, and open minds. The next generation of telescopes will improve sensitivity and resolution. Ground-based observatories with adaptive optics and space telescopes with larger mirrors will capture more light from exoplanets, revealing fainter signals and finer details. Spectroscopy will advance, allowing detection of molecules previously beyond reach. Improved computational models will simulate atmospheric chemistry more accurately, predicting what signatures to expect and how to interpret them. International collaboration accelerates progress. Exoplanet science draws on expertise from astronomy, planetary science, chemistry, biology, and engineering. Sharing data, techniques, and ideas across borders and disciplines maximizes efficiency and minimizes redundancy. Large surveys benefit from coordinated observing campaigns where multiple telescopes target the same systems, building comprehensive datasets that single instruments couldn't achieve alone. Public interest sustains funding and enthusiasm, Exoplanet discoveries capture imagination, making headlines and inspiring new generations of scientists. This engagement translates into support for continued research, ensuring that missions proceed and instruments are built. The search for life elsewhere resonates deeply, connecting scientific inquiry to fundamental questions about existence, purpose, and humanity's cosmic context. Ultimately, the characterization of exoplanets moves beyond cataloging worlds to understanding them. What are they made of? How did they form? Do they have atmospheres? Oceans? Life? Each question answered raises new ones, deepening knowledge and expanding the frontier. The diversity of exoplanets ensures that surprises await, challenging assumptions and revealing nature's creativity across the vastness of space. The search for potential ocean worlds extends beyond the familiar candidates. Several exoplanets exhibit characteristics suggesting massive water content, though confirming liquid oceans beneath thick atmospheres or ice shells remains challenging. Kepler 62f, for instance, orbits a star smaller and cooler than the Sun at a distance that places it in the habitable zone. Models suggest it could be entirely covered by ocean, potentially hundreds of kilometers deep. Such depths would create conditions utterly foreign to Earth's oceans, immense pressures at the bottom forming exotic ice phases that remain solid despite the heat from the planet's interior. These high-pressure ices, like Ice 7 or Ice 10, exist only in laboratory conditions on Earth, but might dominate the deep layers of ocean worlds, creating a stratified environment where liquid water sits atop a solid ice layer, despite temperatures that would normally melt ice. The irony of hot ice isn't lost on scientists. Kepler 442b presents another intriguing case. Larger than Earth but still within the super-Earth category, it orbits a K-type star cooler than our Sun. Its position in the habitable zone and estimated mass suggest it could retain a thick atmosphere and potentially harbour liquid water. Whether that water exists as a global ocean, polar caps, or subsurface reservoirs depends on factors we can't yet measure directly. Atmospheric composition, volcanic activity, magnetic field strength. Each influences whether water remains stable at the surface or escapes into space over geological time. Without direct observation, scientists rely on models that incorporate what we know from solar system bodies, extrapolating to environments we've never visited. The concept of water worlds challenges assumptions about habitability. Initially, scientists assumed oceans were universally beneficial for life, mirroring Earth's reliance on water. But deeper consideration reveals complexities. A planet entirely covered by ocean lacks exposed land, eliminating the rock weathering processes that regulate atmospheric carbon dioxide on Earth. This carbonate-silicate cycle acts as a thermostat, removing excess CO2 through weathering and returning it via volcanic activity. Without land, this feedback loop breaks, potentially leading to runaway greenhouse effects or ice ages depending on atmospheric composition. However, recent research suggests water worlds might maintain habitable conditions through different mechanisms. Thick atmospheres with optimal CO2 levels could sustain liquid water for billions of years without geochemical cycling, as long as initial conditions fall within certain ranges. The universe doesn't require Earth-like processes for habitability. It might achieve stability through alternative pathways. IZ Ceti b, located just 12 light-years away, adds another dimension to ocean world studies. This rocky planet, slightly larger than Earth, orbits a red dwarf star. Its proximity and size make it a prime candidate for atmospheric characterization with current and future telescopes. If it possesses a substantial ocean, studying its atmosphere could reveal how water vapor, clouds, and greenhouse gases interact on a world dominated by liquid water. The challenge lies in distinguishing between a planet with extensive oceans and one with thick clouds obscuring a drier surface. Both scenarios produce similar spectral signatures, requiring careful analysis to differentiate. But the effort is worthwhile. Confirming an ocean world around a nearby red dwarf would suggest such planets are common. Given, red dwarfs constitute 3/4 of all stars. Tidal heating introduces another energy source that expands habitability beyond the traditional zone. When a planet orbits close to its star or experiences gravitational tugs from neighboring planets, tidal forces deform its interior. This flexing generates heat, warming the planet from within. Europa, Enceladus, and other solar system moons demonstrate tidal heating's power, maintaining subsurface oceans despite frigid surface temperatures far beyond the Sun's habitable zone. Exoplanets in compact systems, like TRAPPIST-1, experience significant tidal heating. The innermost planets might have molten mantles or subsurface magma oceans, while outer planets could sustain liquid water beneath ice shells. This internal warmth could compensate for reduced starlight, keeping water liquid even on planets that appear too cold based on stellar radiation alone. The implications for life are profound. Subsurface oceans shielded from stellar radiation avoid surface hazards like UV exposure and atmospheric stripping. Microbes or more complex organisms could thrive in these hidden seas, deriving energy from chemical reactions between water and rock rather than photosynthesis. Earth's hydrothermal vents host ecosystems independent of sunlight, relying on chemosynthesis driven by mineral-rich water from the planet's interior. Similar environments might exist on exoplanets with tidal heating, creating habitable niches undetectable through atmospheric observation. Life could flourish in darkness, far from telescope's view, sheltered beneath ice kilometers thick. Detecting subsurface oceans on exoplanets presents formidable challenges. Unlike atmospheric signatures revealed through spectroscopy, hidden oceans leave indirect clues. Gravitational measurements can hint at internal structure. Low density suggests significant water content, but don't confirm its state. A planet with water distributed as ice throughout its mantle differs from one with a liquid ocean layer, yet both might have similar average densities. Magnetic field detection offers another approach. Liquid water layers, if salty enough, could generate magnetic fields through internal motion, analogous to Jupiter's moons. Detecting such fields from light years away requires extremely sensitive instruments and favorable observing conditions. Alternatively, surface features might betray subsurface oceans. Cryovolcanoes, geysers, or tectonic activity could indicate liquid water beneath, though resolving such details on distant exoplanets exceeds current capabilities. Future missions aim to address these challenges. The upcoming Habitable Worlds Observatory, designed to directly image Earth-sized exoplanets, could detect signs of water vapor escaping from subsurface oceans through surface vents. High-resolution spectroscopy might reveal chemical signatures of ocean-derived compounds in atmospheres, hinting at liquid water below. Combining multiple observations, transit spectroscopy, direct imaging, gravitational measurements, builds comprehensive pictures of individual worlds. No single technique provides definitive answers, but together they constrain possibilities, narrowing the range of plausible scenarios until one emerges as most consistent with all available data. The diversity of exoplanets continually surprises researchers. Hot Jupiters, once thought anomalies, turned out to be relatively common. Super-Earths, absent from our solar system, dominate exoplanet catalogues. Each discovery refines understanding of planetary formation and migration, revealing processes that shape solar systems differently depending on initial conditions. Some gas giants spiral inward through interactions with protoplanetary disks, settling in scorching orbits. Others remain distant, their positions unchanged since formation. Rocky planets can form close to stars or far away, with compositions ranging from iron-rich to carbon-dominated, depending on the materials available in their birth nebulae. This variety suggests that almost any configuration is possible given the right circumstances, with no single template for solar systems. 51 Pegasi b, the first exoplanet discovered around a Sun-like star, exemplifies how observations overturn assumptions. Before its 1995 detection, planetary systems were expected to resemble ours: small rocky worlds near the star, gas giants farther out. Instead, 51 Pegasi b, a gas giant orbiting its star every 4 days, shattered that model. Its existence required new theories of planetary migration, where gas giants form beyond the ice line and migrate inward through disk interactions or gravitational encounters with other planets. This migration explains hot Jupiter's prevalence and suggests our solar system's architecture isn't necessarily typical. Jupiter and Saturn remain distant, avoiding inward migration, but other systems experience different histories, producing configurations unlike ours. Recognizing this diversity prevents biased searches. Assuming all systems resemble ours would miss most exoplanets. The ancient planet PSRB 1620-26b, approximately 12.7 billion years old, offers perspective on planetary longevity. Formed shortly after the universe's birth, it orbits a pulsar and white dwarf in a binary system. This gas giant survived the supernova explosions that created its stellar companions, enduring extreme radiation and gravitational disruptions. Its persistence demonstrates planetary resilience. Worlds can survive stellar deaths, adapting to radically changed environments. The planet's age also raises questions about life's potential timescale. If planets form early in the universe's history and remain stable for billions of years, life could have emerged and evolved on countless worlds long before Earth formed. Ancient civilizations might have risen and fallen while our solar system was still a swirling disk of gas and dust. This humbling thought places humanity's existence in cosmic context. We're latecomers in a universe potentially teeming with older, more advanced life. Planetary atmospheres hold keys to understanding habitability, but interpreting their signals requires caution. Water vapor in an atmosphere doesn't guarantee liquid water on the surface. Venus has water vapor in its atmosphere, yet its surface is a hellish desert. High temperatures cause any surface water to evaporate, but atmospheric conditions prevent it from condensing as rain, trapping it as vapor. Distinguishing between a world with oceans and one with atmospheric water vapor alone requires measuring temperature, pressure, and composition in detail. Pressure determines whether water condenses or remains gaseous at given temperatures. A planet with thick clouds might have extensive oceans below, or those clouds might reflect a runaway greenhouse effect, evaporating all surface water. Context matters. Stellar flux, atmospheric thickness, and greenhouse gas concentrations all influence outcomes. Tidal locking, where one side of a planet permanently faces its star, complicates habitability assessments. TRAPPIST. 1e and many exoplanets around red dwarfs are tidally locked, creating extreme temperature contrasts between day and night sides. The day side bakes under constant starlight while the night side freezes in perpetual darkness. This dichotomy could render planets uninhabitable if atmospheres can't redistribute heat effectively. However, simulations suggest that thick atmospheres can transport heat from day to night sides, moderating extremes and creating twilight zones at the boundary where conditions might support liquid water. Alternatively, subsurface oceans could provide thermal inertia, buffering surface temperatures and maintaining habitability despite tidal locking. The question remains open. Tidally locked, planets might be habitable under certain conditions, but whether those conditions exist frequently or rarely is unknown. The search for biosignatures focuses on atmospheric gases that indicate biological activity. Oxygen, when combined with methane, suggests life because these gases react and wouldn't coexist in large quantities without continuous replenishment. On Earth, photosynthesis produces oxygen, while biological processes produce methane, maintaining both in the atmosphere. Detecting this combination on an exoplanet would strongly suggest life. though false positives are possible. Abiotic processes can produce oxygen or methane individually, so finding both together and in disequilibrium strengthens the case. Other potential biosignatures include phosphine, dimethyl sulfide, or specific isotopic ratios that favor biological origins. Each signature has limitations and ambiguities, requiring multiple lines of evidence to build convincing cases for life. Technology advances drive progress in exoplanet characterization. Early detections relied on radial velocity and transit methods, which reveal planetary presence and basic properties, but limited atmospheric information. Modern spectroscopy during transits captures starlight filtered through exoplanet atmospheres, revealing molecular absorption features. Next-generation telescopes like the Extremely Large Telescope and the Habitable Worlds Observatory will improve sensitivity and resolution, detecting fainter signals and resolving finer details. Direct imaging, capturing light reflected or emitted by planets themselves, will become feasible for more targets, providing complementary data to transit spectroscopy. Combining techniques maximizes information extracted from observations, painting fuller pictures of distant worlds. Computational models play crucial roles in interpreting observations. Simulating exoplanet atmospheres requires accounting for chemistry, dynamics, and radiation transfer. Models predict how different atmospheric compositions respond to stellar radiation, which molecules form under various conditions, and how clouds and hazes affect spectral features. Comparing model predictions to observations constrains atmospheric properties, narrowing possibilities until one scenario matches data best. However, models have limitations. They rely on assumptions about physics and chemistry that might not hold under all conditions. Exotic chemistries or unknown processes could produce unexpected signals, leading to misinterpretations. Continuously refining models with new data and laboratory experiments improves accuracy, but uncertainty remains inherent. International collaboration accelerates exoplanet research. Missions like JWST involve contributions from NASA, ESA, and CSA, pooling resources and expertise. Ground-based observatories coordinate observing campaigns, targeting the same systems with multiple instruments to build comprehensive datasets. Data sharing allows researchers worldwide to analyze observations, bringing diverse perspectives and techniques to bear on problems. This collaborative approach maximizes efficiency, reduces redundancy, and ensures that discoveries benefit from collective knowledge. Exoplanet science transcends borders, uniting humanity in exploring the cosmos. Public engagement sustains momentum for exoplanet research. Discoveries capture imagination, inspiring new generations to pursue science. Outreach programs, educational resources, and media coverage translate technical findings into accessible narratives, connecting research to broader audiences. This engagement fosters support for continued funding, ensuring missions proceed and instruments are built. The search for life elsewhere resonates deeply, tapping into fundamental questions about existence and humanity's place in the universe. Sustaining public interest maintains the societal investment necessary for long-term projects spanning decades. The diversity of exoplanets ensures that surprises await. Each new detection, each refined measurement, each unexpected signal pushes boundaries of understanding. Nature's creativity exceeds human imagination, producing worlds unlike anything anticipated. Some planets orbit binary stars, experiencing complex stellar dynamics. Others drift through space without stars, ejected from their birth systems and wandering the galaxy alone. A few might have rings, moons, or magnetic fields that create unique environments. Exploring this diversity reveals the full range of planetary possibilities, showing what nature can create given different starting conditions and evolutionary histories. Ultimately, Exoplanet characterization moves beyond cataloging worlds to understanding them deeply. What processes shaped their atmospheres? How do their interiors influence surfaces? Do they host life, past or present? Each question answered raises new ones, deepening knowledge while expanding frontiers. The journey from detecting exoplanets to characterizing them thoroughly continues, driven by curiosity and enabled by advancing technology. The universe offers infinite complexity, and humanity has barely begun to unravel it. Contemplating life beyond Earth requires rethinking assumptions about habitability. Traditional models centered on Earth-like conditions, rocky surfaces, oxygen-rich atmospheres, temperate climates. But discoveries expand possibilities. Water worlds, planets entirely covered by deep oceans, challenge land-centric views. Subsurface oceans beneath icy shells, warmed by tidal heating or radioactive decay, offer hidden refuges where life might flourish without sunlight. Even atmospheres once considered inhospitable could support exotic biochemistries adapted to different chemistries. Life's resilience on Earth, thriving in acidic hot springs, frozen tundra, and deep ocean vents, hints at potential adaptability elsewhere. Defining habitability broadly increases targets worth investigating, acknowledging that life might surprise us. TRAPPIST. One exemplifies systems demanding closer scrutiny. 7 Earth-sized planets orbit a cool red dwarf star, with several residing in the habitable zone. This compact system resembles Jupiter and its moons more than our solar system, with all 7 worlds fitting inside Mercury's orbit. Gravitational interactions between neighboring planets create tidal heating, potentially melting interiors and driving geological activity. TRAPPIST-1e, the most Earth-like candidate, receives about 60% of the starlight Earth does, but its star appears 4 times larger in the sky, casting a perpetual reddish twilight. Observations suggest some planets might harbor water, though atmospheric properties remain uncertain. Red dwarf stars like TRAPPIST-1 are abundant, making up 3/4 of all stars in the galaxy. If planets around red dwarfs can maintain atmospheres and liquid water despite stellar flares and radiation, habitable worlds multiply dramatically. Understanding TRAPPIST-1 informs predictions about countless similar systems scattered throughout space. Proxima Centauri b, our nearest exoplanetary neighbor, lies just over 4 light-years away. This rocky world orbits within its star's habitable zone, where temperatures might permit liquid water. Proximity makes it a prime candidate for detailed study and future exploration. Even so, the distance translates to over 25 trillion miles, far beyond current spacecraft capabilities. Reaching Proxima Centauri b would require revolutionary propulsion technologies or multi-generational missions spanning millennia. Yet its closeness, astronomically speaking, offers unique opportunities. Light from Proxima Centauri reaches us in just over 4 years, allowing relatively rapid feedback for observations. Future missions might send lightweight probes accelerated to significant fractions of light speed, arriving within decades and transmitting data back to Earth. Such missions remain speculative, but Proxima Centauri b's nearness makes it the most plausible first target for interstellar exploration. Water worlds represent another intriguing category. These planets possess oceans covering their entire surfaces, potentially hundreds or thousands of kilometers deep. Unlike Earth, where continents and seafloors interact, water worlds lack exposed land. Their oceans might extend down to high-pressure ice layers, creating exotic structures beneath the waves. Some scientists question whether water worlds could support life, arguing that the carbonate-silicate cycle, which regulates Earth's climate through interactions between atmosphere, ocean, and crust, requires exposed rock. Without this cycle, carbon dioxide levels might spiral out of control, either freezing the planet or triggering runaway greenhouse effects. However, Other researchers suggest that water worlds could maintain stable conditions through alternative mechanisms. Atmospheric properties on water worlds might naturally fall into a sweet spot, allowing billions of years of habitability without geological cycling. Subsurface interactions between water and rocky cores could also regulate chemistry, providing nutrients and energy sources for potential biospheres. Kepler-62f, Kepler-452b, and Kepler-442b are candidates for water worlds, with compositions suggesting substantial water content. These distant planets, hundreds or thousands of light-years away, remain largely mysterious. Observations reveal sizes, masses, and orbital parameters, but atmospheric compositions and surface conditions remain speculative. Future telescopes might detect water vapor signatures or other atmospheric features, confirming or refuting water world hypotheses. If confirmed, water worlds would represent entirely new environments for life, demanding reconsideration of biology's requirements. Imagining life in endless oceans, perhaps floating near surfaces or dwelling in deep, high-pressure layers, expands conceptual boundaries. Subsurface oceans offer another pathway to habitability. Icy moons in our solar system, like Europa and Enceladus, harbor liquid water beneath frozen crusts. Tidal heating from gravitational interactions with parent planets keeps these oceans liquid despite freezing surface temperatures. Europa's ocean, tens of kilometers deep, might contain more water than all of Earth's oceans combined. Hydrothermal vents on Europa's seafloor could provide energy and nutrients, similar to vents on Earth that support entire ecosystems without sunlight. Exoplanets might also possess subsurface oceans, warmed by internal heat sources. Detecting these hidden seas presents challenges, as they don't produce obvious atmospheric signatures. However, indirect evidence, like magnetic fields generated by salty oceans or surface features indicating geological activity, could hint at their presence. Tidal heating plays a crucial role in maintaining subsurface oceans. When a planet or moon orbits close to a larger body, gravitational forces stretch and squeeze it, generating friction and heat. This process keeps interiors warm, even far from the star. In the TRAPPIST-1 system, tidal interactions between neighboring planets create significant heating, potentially melting mantles and forming subsurface magma oceans. These internal heat sources might sustain liquid water beneath icy surfaces, creating habitable environments independent of stellar radiation. Tidal heating extends the range of potentially habitable worlds beyond traditional habitable zones, encompassing icy planets and moons that would otherwise seem too cold for life. Red dwarf stars dominate the galaxy, but their planets face unique challenges. Red dwarfs emit most of their energy as infrared radiation, providing little visible light. Planets in habitable zones orbit close to these dim stars, experiencing strong tidal forces that often lock them, keeping one side perpetually facing the star while the other remains in darkness. This configuration creates extreme temperature gradients, with the day side scorching and the night side freezing. Atmospheric circulation might redistribute heat, moderating extremes, but this depends on atmospheric properties and planetary characteristics. Red dwarfs also exhibit frequent flares, releasing bursts of high-energy radiation that could strip atmospheres and sterilize surfaces. Despite these challenges, red dwarfs are abundant and long-lived, offering billions of years for life to emerge and adapt. If even a small fraction of red dwarf planets host life, the galaxy teems with inhabited worlds. Atmospheric retention determines long-term habitability. Planets must retain atmospheres over billions of years for life to develop and persist. Stellar winds, especially from active stars like red dwarfs, erode atmospheres through a process called atmospheric escape. Light gases like hydrogen and helium escape easily, but heavier molecules can also be lost over time. Magnetic fields provide protection, deflecting stellar wind and reducing escape rates. Earth's magnetic field shields its atmosphere, but Mars, lacking a global magnetic field, lost much of its atmosphere to space. Exoplanets around active stars face similar risks. However, some planets might replenish atmospheres through volcanic outgassing or other geological processes, balancing losses and maintaining conditions suitable for life. Direct imaging represents a frontier in exoplanet observation. Unlike transit methods, which detect planets indirectly, direct imaging captures light from the planets themselves. This technique requires blocking overwhelming starlight to reveal faint planetary signals. Coronagraphs and star shades achieve this, creating artificial eclipses that allow telescopes to see planets nearby. Direct imaging provides complementary data to spectroscopy, revealing reflected light or thermal emission from planets. Analyzing this light reveals atmospheric properties, surface features, and even seasonal variations. Currently, direct imaging targets mostly large, young planets orbiting far from bright stars, where contrasts are manageable. Future telescopes will improve sensitivity, enabling direct imaging of smaller, cooler planets, including Earth-sized worlds and habitable zones. The extremely large telescope, under construction, will dramatically enhance observational capabilities. With a mirror over 30 meters in diameter, it will gather more light than any existing telescope, resolving finer details and detecting fainter signals. This increased sensitivity will enable characterization of more exoplanet atmospheres, including those of smaller planets that current instruments struggle to observe. The extremely large telescope will also perform direct imaging of exoplanets, capturing reflected light and thermal emission to study atmospheric compositions and dynamics. Its observations will complement space-based missions, providing ground-based perspectives that enhance understanding of distant worlds. The Habitable Worlds Observatory, a proposed NASA mission, aims to directly image Earth-like exoplanets in habitable zones. Equipped with advanced coronagraphs and spectrographs, it will search for biosignatures in planetary atmospheres, specifically targeting oxygen, methane, and other molecules associated with life. The mission's design prioritizes stability and precision, ensuring that faint planetary signals aren't lost in noise. If successful, the Habitable Worlds Observatory could provide the first definitive evidence of life beyond Earth, transforming humanity's understanding of its place in the universe. Planning for such missions requires decades of preparation, developing technologies, and building international collaborations to support ambitious goals. Biosignatures, indicators of life, guide searches for inhabited worlds. Oxygen, produced by photosynthesis on Earth, is a strong biosignature, but other processes can generate oxygen without life. Methane, another candidate, can result from biological or geological sources. Detecting both oxygen and methane together strengthens the case for life, as their coexistence in an atmosphere suggests ongoing biological production. Other potential biosignatures include phosphine, dimethyl sulfide, or even artificial chemicals like chlorofluorocarbons, which on Earth are produced industrially. However, interpreting biosignatures requires caution. Abiotic processes might mimic biological signals, leading to false positives. Conversely, life might produce unexpected signatures, causing researchers to overlook evidence. Developing frameworks for interpreting biosignatures involves studying Earth's biosphere, simulating alien chemistries, and considering diverse forms life might take. False positives complicate biosignature detection. Venus, for example, has trace amounts of phosphine, a molecule often associated with life. However, volcanic activity or atmospheric chemistry could produce phosphine without biology. Similarly, oxygen can result from photodissociation of water vapor, where ultraviolet light breaks water molecules apart, releasing oxygen. Without biological processes to replenish methane, atmospheres dominated by oxygen might indicate abiotic chemistry rather than life. Distinguishing true biosignatures from false positives requires comprehensive atmospheric characterization, measuring multiple molecules and understanding their interactions. Context matters. Knowing a planet's history, stellar environment, and geological activity helps interpret observations accurately. Technosignatures, signs of technological civilizations, represent another search avenue. While biosignatures indicate life's presence, technosignatures reveal intelligence and technology. Radio signals, laser pulses, or artificial structures like megastructures could betray advanced civilizations. CT, the search for extraterrestrial intelligence, scans skies for such signals, listening for patterns that natural processes couldn't produce. So far, no confirmed technosignatures have been detected, but searches continue, expanding in scope and sensitivity. Some researchers propose looking for industrial pollutants in exoplanet atmospheres, chemicals like chlorofluorocarbons that indicate technological activity. Others suggest searching for waste heat from energy-intensive civilizations or optical signatures from massive engineering projects. Technosignatures offer tantalizing possibilities, but their absence doesn't imply life's rarity. Civilizations might be short-lived, technologically undetectable, or simply distant. Philosophical implications accompany exoplanet discoveries. Finding life elsewhere would answer one of humanity's oldest questions, confirming that life isn't unique to Earth. This discovery would reshape worldviews, religious beliefs, and humanity's sense of significance. Conversely, finding no life despite extensive searches might suggest life's rarity, emphasizing Earth's uniqueness and fragility. Either outcome carries profound meaning. The search itself, regardless of results, reflects humanity's curiosity and drive to understand the universe. It unites people across borders, cultures, and disciplines, fostering collaboration and shared purpose. Exoplanet research transcends science, touching on philosophy, ethics, and humanity's future. Public engagement sustains momentum for these endeavors. Discoveries capture imaginations, inspiring young people to pursue science and fostering societal support for funding missions. Outreach programs, educational resources, and media coverage translate technical findings into accessible narratives, connecting research to broader audiences. This engagement ensures continued investment in long-term projects spanning decades. The search for life resonates deeply, tapping into fundamental questions about existence and humanity's place in the cosmos. Maintaining public interest sustains the societal will necessary for ambitious missions. Ultimately, characterizing exoplanets moves beyond cataloging worlds to understanding them. What shaped their atmospheres? How do interiors influence surfaces? Do they host life? Each answer raises new questions, deepening knowledge while expanding frontiers. The journey from detecting exoplanets to characterizing them thoroughly continues, driven by curiosity and enabled by advancing technology. Humanity stands at the threshold of discovering whether life exists elsewhere, a question that will define this era of exploration. The universe offers infinite complexity, and we've barely begun to unravel it. Every observation, every refined measurement, every unexpected signal pushes understanding forward, revealing nature's creativity in producing worlds beyond imagination. The sheer scale of what we've discovered in just 3 decades is staggering when you let it settle. 6,000 confirmed worlds. Billions more waiting to be found. Each one a complete system of physics, chemistry, and possibility. Some are scorching giants racing around dying stars. Others are frozen rocks drifting in darkness. A few might be ocean worlds where waves have never touched shore. And somewhere among them, perhaps on a planet we've already detected but not yet characterized, life might be looking back. We're living through a unique moment in human history. For most of our existence, We wondered whether planets existed beyond our solar system. Now we know they're everywhere. The question has shifted from, are there other worlds, to what are those worlds like? And eventually, inevitably, to, is anyone else out there? The tools we have now would have seemed impossible just a generation ago. Telescopes that can taste the air of planets 40 light years away. Instruments sensitive enough to detect the chemical fingerprint of water vapor or methane in the faint glow of starlight filtered through alien atmospheres. Computers that can model entire planetary climates, predicting how heat flows, how gases interact, how life might alter the chemistry of a world. Each technological leap brings us closer to answering questions that once belonged only to philosophy. But what strikes me most isn't the sophistication of the technology, it's the patience required. Characterizing a single exoplanet thoroughly can take years of observations. Building and launching a new telescope might consume a decade or more. Analyzing the data, ruling out false positives, confirming unexpected findings. All of this moves at the careful pace of rigorous science. There are no shortcuts to understanding worlds separated from us by light years of empty space. And yet, the work continues. Teams around the world coordinate observations, share data, refine models. Students who weren't born when the first exoplanet was discovered now led research projects characterizing atmospheres or searching for biosignatures. The knowledge accumulates slowly but steadily, each paper adding another piece to an incomplete but growing picture. TRAPPIST-1 might harbor liquid water on several of its worlds. Proxima Centauri b could be a rocky planet with an atmosphere. Some distant super-Earth might be covered entirely by a global ocean kilometers deep. We don't know yet. But we're getting closer. Every observation narrows the possibilities. Every new technique reveals details previously hidden. The answers are there, waiting in the light that's been traveling toward us for decades or centuries, carrying information about worlds we're only beginning to understand. If we do find life, whether through a biosignature in an atmosphere, a technosignature from a distant civilization, or eventually through direct exploration of nearby systems, it will fundamentally alter our perspective. Not just scientifically, but philosophically. The realization that we're not alone would ripple through every aspect of human thought, affecting how we see ourselves, our planet, and our responsibilities to both. But even if we search for generations and find nothing, that outcome carries meaning too. It would suggest that life, at least intelligent technological life, is exceedingly rare. That Earth represents something precious and fragile, a spark of complexity in a universe that leans toward simplicity. That protection of the biosphere isn't just an environmental concern, but a cosmic imperative. The search itself matters regardless of the outcome. It represents humanity at its best, curious, collaborative, reaching beyond immediate concerns toward questions that transcend any single lifetime. It's a project that will outlive everyone currently working on it, passing from one generation of scientists to the next, building on accumulated knowledge and improved technology. Right now, starlight from distant planets is streaming through space toward Earth. Some of that light left its source before humans existed. Some began its journey while dinosaurs walked the planet. And some, from the nearest systems, started traveling toward us just a few years ago. That light carries information about atmospheric composition, surface temperature, the presence of water or methane or oxygen. When it finally reaches our telescopes and is analyzed by instruments we've built specifically to decode its secrets, it will tell us something new about worlds we've never visited and might never reach. The universe is larger and stranger than our ancestors imagined, more diverse in its planetary systems, more varied in the environments it creates, more surprising in the ways physics and chemistry combine to produce complexity. We've only just begun mapping this diversity, cataloging the types of worlds that exist, and starting to understand the processes that shape them. Somewhere out there, orbiting a red dwarf star in a compact system, a tidally locked planet bathes in perpetual twilight. On another world, maybe ice kilometers thick shields a dark ocean where volcanic vents warm the water and complex chemistry unfolds in complete darkness. On yet another, possibly, photosynthesis, or something like it, produces oxygen that accumulates in the atmosphere, waiting for us to detect it and recognize what it means. These worlds exist whether we discover them or not. They orbit their stars, evolve through geological time, respond to the forces that shape all matter. Our observations don't create them. They simply reveal what was already there, adding another data point to our growing understanding of planetary systems and the possibilities they contain. The exoplanets we've found so far represent just the beginning. The vast majority of worlds in the galaxy remain undetected, their secrets preserved by distance and the limitations of current technology. But those limitations are temporary. Each new telescope, each improved technique, each refined model expands what we can see and understand. The frontier keeps moving outward, encompassing more systems, characterizing more atmospheres, searching more thoroughly for signs of life. And so the work continues. Observations are scheduled, data is analyzed, papers are written and reviewed. New students enter the field, bringing fresh perspectives and ideas. International collaborations form and evolve. Public interest sustains funding and enthusiasm. The machinery of scientific progress, slow and methodical, but remarkably effective, grinds forward. 30 years ago, we confirmed the first exoplanet around a sun-like star. 30 years from now, we might have characterized dozens of potentially habitable worlds, detected biosignatures in multiple atmospheres, or even received a techno-signature from a civilization we never knew existed. Or we might still be searching, refining our methods, ruling out false positives, and building the next generation of instruments that will finally provide the sensitivity needed for definitive answers. Either way, the questions that drive this search: are we alone? What kinds of worlds exist? Where might life arise? Will continue pulling us forward. They're too fundamental to ignore, too compelling to abandon. As long as humans look up at the night sky and wonder what lies beyond, the search for exoplanets and the life they might harbor will persist. The universe has offered us a gift in these 6,000 worlds we've discovered. Not answers, necessarily, but possibilities. Each planet is a reminder that nature's creativity extends far beyond what we see around us, that the cosmos produces endless variations on planetary themes, from scorched giants to frozen dwarfs, from water worlds to worlds of exotic ice, from atmospheres thick enough to crush metal to surfaces exposed directly to vacuum. And among all that diversity, somewhere, perhaps life found a foothold. Perhaps it emerged from chemistry, organized itself into self-replicating systems, evolved and adapted and persisted for billions of years. Perhaps it developed complexity, intelligence, technology. Perhaps it's out there now, looking at our sun as a distant point of light, wondering the same things we wonder. We don't know yet, but we're looking, and that in itself feels like enough.